If you've watched the first part of this video, then you should have answered this question. If you haven't done that, you should really go back and watch that. Now, if you've answered the question, let's see the answer. Let's see that again in slow motion, shall we? So if you predicted that they both hit the ground at the same time, you were right. But a lot of people would have predicted that the heavier one hits the ground first. So what we've just seen with those two masses is that the acceleration of falling objects is independent of mass. Except you can probably think of counterexamples. So now I'm going to drop a coin and a feather. And clearly those didn't fall with the same acceleration. But now I've got the feather inside a sealed jar. And I've connected that jar by this hose to a vacuum pump. And if I now evacuate the jar, now we see a rather different result when I drop them both. The issue with the feather, of course, is air drag. Technically, we don't even call a motion free fall unless it's only under the influence of gravity. So really, the coin wasn't quite in free fall either, because there's air drag on it too, but that air drag on the coin is negligible compared to the gravitational influence. The acceleration of falling objects that's mass independent we call g, and that's the acceleration due to gravity. And the acceleration due to gravity varies a bit from place to place, but it's about 9.8 meters per second squared. Note, it's not negative. You can talk about your vertical component of acceleration, and if you set your y-axis up, then it'll be negative 9.8 meters per second squared. But of course, as usual, whether this thing is positive or negative depends on your choice of axes. And also, it does vary from place to place. You'll find textbooks often quoted as 9.81 meters per second squared, but that's a little bit silly. To 2 sig figs, it's 9.8 meters per second squared everywhere on Earth. But it does vary from place to place. Here's a map showing that variation. And the third sig fig is different depending on where you are in the world. Well, now I'm going to do something that I haven't done very much in these video lectures. I'm going to derive some equations. And I want to make a point. First of all, I don't think it's important that you memorize these equations. You can look them up when you need them. Second of all, I don't expect you to be able to repeat this derivation. I'll never ask you to do this derivation on an exam or anything. So why am I bothering with this derivation? Well, a few reasons. The main one, though, is that I think it's important that you see that these equations just come from the definitions that we've already done. So they don't come out of thin air. They come from things we've been discussing and methods that we know. So look at them not as a derivation to learn, but as a demonstration of the power of the ideas we've been using. So we've got, for constant acceleration, where we can drop the average here, this ax is delta vx over delta t. Well, let's just rearrange that. And this is going to be a lot like another rearrangement of an equation I did a couple of lectures ago. So we'll remember that that delta vx is a final minus an initial, and so we'll just do that replacement and bring the initial over to the other side of the equation. Now, if we again just let ti be 0, we're talking about some later tf, might as well just call it t, and as long as we're calling that t, we might as well call our final vx just plain old vx. So now we have the equation in this form, and again, so what? Well, again, we've got ourselves an equation that's in the same form as the regular equation for a straight line. So this is telling us something we already knew, which is that the vx versus t graph for constant acceleration must be a straight line. But moreover, we can see how we can just read the intercept off of it, and we already knew the slope had to be the acceleration. But now let's do something else with this. What if we want to know delta x, the x component of displacement, between some ti and tf? Okay, well I need to back up a bit because I'm no longer just letting ti be 0 and renaming tft. So let me return to this form of the equation. And I know, I told you a couple of lectures ago, that we can always calculate the displacement by the area under the v versus t graph. Now, for non-constant v, I haven't proved that to you, and I will eventually, but it's not time to prove it to you yet. So for the moment, you're going to have to take my word for it for a while longer. But let's go ahead and do that. We've got this area under the vx versus t graph. How are we going to do that? Well, we can split this area up into a rectangle and a triangle. So all we need to do is find the area of the rectangle and the triangle and add them together. So let's do that. First of all, let's note that this distance here, which isn't a distance, it's a time, but anyway, it's the base of the rectangle and of the triangle, and it's delta t. This total height here is vxf. And this total height here is vxi, which means the little bit on the top, which is the height of the triangle, must be vxf minus vxi. But look at that. That's just delta v. And delta v we can rewrite as ax delta t. So now we can start putting together these areas. The area of the rectangle is just going to be its height times its width, so vxi times delta t. And the area of the triangle is a half times its height times its width, and so a half ax delta t times delta t, which we can simplify. And so our total displacement, or x component of displacement, is just the sum of those two things. And there's our new equation. And I'll just say you can get one more equation quite easily, and I'm going to leave it to you to do it as an exercise. All you need to do is solve for delta t out of one of those two equations and plug it into the other and do some rearranging, and you'll get this one. And now we have three equations, which I will call the equations of uniformly accelerated motion. And we'll spend next lecture looking at how to solve problems using these.